Today we're exploring one of the most famous and misunderstood concepts in human genetics, mitochondrial Eve. Despite what many people believe, she was not the first woman. She was not the only woman alive, and she certainly wasn't the biblical Eve. Instead, she represents the woman whose mitochondrial DNA survives in every living person today through an unbroken maternal line. Understanding why that happened opens a fascinating window into population genetics, evolution, and our shared human ancestry. Most people think of DNA as the chromosomes inside the nucleus. But every one of your cells also contains hundreds or even thousands of tiny mitochondria. These structures have their own DNA. Unlike nuclear DNA, mitochondrial DNA is inherited almost exclusively from your mother. Every child receives mitochondrial DNA from their mother, but only daughters pass it on to the next generation. That simple inheritance pattern makes mitochondrial DNA an incredibly powerful tool for reconstructing maternal ancestry over thousands of generations. Because mitochondrial DNA passes directly from mother to child without recombination, it changes very little over time. Instead of being shuffled every generation like nuclear DNA, mitochondrial DNA accumulates only occasional mutations. Those rare mutations become genetic markers that allow scientists to identify branches of humanity stretching back tens of thousands of years. It's almost like reading tiny spelling changes in a manuscript copied over thousands of generations. Every time a new mutation occurred in one woman's mitochondrial DNA, her descendants inherited that change. If her maternal line survived through time, that mutation became the defining marker of a new haplogroup. A haplogroup is simply a large branch on humanity's maternal family tree. Today, scientists have identified hundreds of mitochondrial haplogroups that reveal ancient migrations across Africa, Europe, Asia, Oceania, and the Americas. Imagine taking every person alive today and tracing only their mother's mother, then her mother, and so on. Eventually, many of those lines merge. Keep tracing long enough, and eventually every surviving maternal lineage converges on one woman. That woman is what scientists call mitochondrial Eve. This process is known as coalescent theory. Instead of moving forward through time, scientists work backward. Each generation eliminates some maternal lines simply because some women have no daughters, while others have daughters whose lines continue. Eventually, only one maternal lineage remains. This is a mathematical expectation of inheritance, not evidence that only one woman existed. This is where many popular articles unintentionally confuse readers. Mitochondrial Eve was not the first human woman. She lived among thousands of other women. Those women had children. Many had daughters. But over thousands of generations, their purely maternal lines eventually ended. Only one maternal lineage survived continuously into every living person today. Maternal lineages disappear surprisingly easily. A woman may have only sons. Her daughters may have no children. Entire families may die during famine, disease, or migration. Over enough generations, even very large families can lose their uninterrupted maternal line. This happens naturally through the randomness of inheritance. Current evidence suggests mitochondrial Eve lived in Africa approximately 150,000 to 200,000 years ago. That estimate continues to improve as scientists sequence additional ancient genomes and refine mutation rates. Her exact location, appearance, language, and culture remain unknown. What matters is that every living person's maternal line ultimately traces back to her. Mitochondrial DNA follows only one ancestral path. Go back 10 generations and you have over 1,000 genealogical ancestors. Only one of them contributed your mitochondrial DNA. So while mitochondrial DNA is incredibly valuable, it's only one thread in the much larger tapestry of human ancestry.